Day 92 notes, Advanced Algebra 2. Today we finish out our week, our discussion on functions. This time we're looking at the operations with functions. So much like our operations work with numeric values, operations also exist within functions as well. So we can use the shortcut PEMDAS to complete our order of operations using functions. Anytime I'm presented with a series of functions that have to be combined using mathematical operations, I still follow this acronym: parentheses, exponents, multiplication, division, addition, and subtraction. So if I wanted to add together two functions, f and g, I could do so. If I wanted to subtract, multiply, or divide them, that's possible as well. Even if I wanted to take a function and raise it to another power, we can do that. We have the mathematical ability to do so. A more complex example might look something like this, where we have an addition, a division, a set of parentheses, and a power all rolled into one. We still have to follow our order of operations, however, and look at our parentheses first. Within the parentheses, we again follow our order of operations, and inside here, we have an exponent that can be resolved. Following the exponent, we would divide the results, g of x, by the result of h of x to the I of x power. And after this parentheses group has been completed, we can then add it to our function f. When we complete operations with functions, we really have two options to finish the problem. We can either resolve the function first, or we can evaluate each function component. So we're going to work through a couple examples here, and I'll show you both methods in order to simplify function work. Suppose we have a function f of x that's defined as x plus 2, and we have a function g of x that's defined as x minus 7. If we're going to evaluate the operations from above, from these examples here, using an x equal to 3, we can evaluate each of these two functions, f of x plus g of x and f of x minus g of x. Let's work on resolving the function first, and I'll show you what I mean by that. Resolving the function says that if I provide to you a command, f of x plus g of x, we can immediately see what these functions are actually equivalent to. Now, f of x was simply equal to x plus 2. And to add to that, g of x, that was x minus 7. To resolve this function, we could combine like terms. From this group here, x plus x is 2x. And from this first group, 2 plus a negative 7 is equal to negative 5. Therefore, now if I wanted to evaluate this function at x equals 3, I can multiply 2 times 3 and subtract 5. Since our two functions were resolved into one, my final answer is going to be 6 minus 5, which is equal to 1. Similarly, I can resolve the calculation f of x minus g of x, and then evaluate it when x is equal to 3. Again, f of x was x plus 2. Subtract from it g of x, which was x minus 7. X minus x is 0. 2 minus negative 7 is a positive 9. This result is 9. And what's interesting about this is that the solution to this function, or this operation with functions, is going to be 9 regardless of what x is. There is no input value x to affect the result of this function, which is a little bit different than the function we saw over here. X will always have an effect on this function. Now, if we were to complete this by component, our approach is slightly different, but we'll still achieve the same answer. By component, that says we should evaluate what f of 3 is first, and then add to it what g of 3 is. In this case, f of 3, that's got to be 3 plus 2. And adding to that, we need g of 3. That's 3 minus 7. These two must be added together. 3 plus 2 is 5, and we'll add to it a negative, not 7, but a negative 4, because 3 minus 7 is negative 4. And you'll see here that 5 plus negative 4 is 1. This solution matches the solution that we achieved over here when we first resolved the function. So adding by component is the same as resolving the function initially. For the subtraction, I would need f of 3 minus g of 3. F of 3 is 3 plus 2 minus g of 3. G of 3 is 3 minus 7. 5 minus negative 4 is equal to 9. The exact same answer that we saw before when we resolved the function. So completing by component, we're completing by resolving the function together. The result will end up to be the same when we evaluate at a particular value. In this case, it was x equals 3. Let's see another example. In this case, we have f of x times g of x. Well, again, we said that f of x was equal to x plus 2. So if I wanted to multiply f of x times g of x by resolving the functions, I must find f of x times g of x. Now, fortunately, we can complete this calculation. X plus 2 times x minus 7 requires us to FOIL. So that's an x squared plus a negative 7x plus a 2x minus 14. This reduces to x squared minus 5x minus 14. And now I can evaluate when x is equal to 3. I'll change my x's to 3. 3 squared minus 5 times 3 minus 14. And again, this 3 came from the directive at the beginning. We're evaluating each of these when x is equal to 3. This 3 squared becomes 9, minus 15, minus 14. And this result comes out to be negative 20. So when we solve this by resolving, we see that the result is 20. Resolving the function with division in this case can be a little bit more difficult. For example, if I try to divide f of x by g of x, I'm really thinking of the fraction x plus 2 divided by x minus 7. There really is no way for us to resolve this. Even trying to use synthetic division isn't going to get us very far. So all that we can do at this point is solve by component, really. At this point, we can replace the letter x with the number 3, and we would have 3 plus 2 divided by 3 minus 7. This 3 plus 2 reduces to 5. We could divide by negative 4. Can't really simplify this fraction any further. It's improper, so we can try to make it into a mixed number, but really I'm okay with this improper fraction. Negative 5/4 would be a fine solution. If I were to try to answer that first equation by components, then I need to imagine f of 3 times g of 3. So again, I'm looking at the function 3 plus 2 times 3 minus 7. Well, 3 plus 2 is 5. 3 minus 7 is negative 4. When I multiply the two together, I finish with negative 20. Again, the same result that we got by resolving the function first and then simplifying. If I were to resolve the function in division, we'll see that our process is very similar to the method that I've already shown here. F of 3 divided by g of 3. Well, f of 3 we said was 3 plus 2 divided by 3 minus 7. 5 divided by negative 4 is simply negative 5/4. The same result that we got by resolving the fraction first. Now we're looking at an even more complicated problem. F of x raised to the power g of x. Now this one really has no benefit in resolving the function. There's almost no way for us to resolve f of x raised to the g of x power. This would be us trying to answer the question, what is x plus 2 raised to the x minus 7 power? And while in later classes we'll learn how to handle these exponents when we have a variable in the base or if we have a variable in the exponent, it's very difficult to evaluate these functions when you have a variable or a letter x in both the base value and the exponent. So as far as resolving goes, we're not going to approach anything like this. However, we can consider how to solve this by looking at each component. Again, if I was asked to solve f of x raised to the g of x power, evaluate it when x is equal to 3, then I'll just think, what is f of 3? And I'll raise that to the result g of 3. Well, f of 3 is 3 plus 2. G of 3 is 3 minus 7. This would be the number 5 raised to the negative 4th power. And if you remember our exponent rules from earlier in the year, this would be 1 over 5 to the 4th power. I can make this a positive exponent if I move it to the bottom of a denominator. And then I'll just multiply 5 times itself 4 times in a row. And to do that, I'm thinking to myself, well, this is 5 squared times 5 squared. That's 25 times 25, and I remember from my power rules, from my squaring values, 25 times 25 is 625. And we have now completed this problem when x is equal to 3 by solving each component first. We'll finish out this video with one final example. In the event that we're asked to evaluate our functions at two different values, for example, h in this case must be evaluated at the number 1, and I must be evaluated at the number 3, it's really best to complete this by component only. Again, if the two functions are being evaluated at a different position, and they're actually going to be different than the functions f and g, which were evaluated at 3, then it's always a good idea to evaluate these by component first. So let's see what we can get by working through this problem. F of x, through our examples here, has been evaluated at 3 each time. We'll add to it the result of g of 3, because g has been evaluated at 3 as well. We'll divide that by h of 1. That's raised to I of 3. So let's see what we get. F of 3, the function evaluated at 3, well, again, we've seen that all along. That's 3 plus 2. We'll add to that the result of g of 3. Well, that's been 3 minus 7 all along. We will divide h of 1. Now, this is our first new function in a while. When I evaluate 1 inside the function h, I need to think 1 squared minus 1. So that takes care of my h function. And I'll add to that, I'll raise to the power of I evaluated at 3. Well, the function I is x cubed, so I need to take my input value 3 and cube that. 3 plus 2 is 5. We can resolve that piece. 3 minus 7 is negative 4. 1 squared minus 1 is 0. And 3 cubed is 27. Following the order of operations, I would complete my exponents first inside the innermost parentheses. So I'm not going to touch any of my other numbers just yet. I'm only going to simplify this piece, 0 to the 27th power. And that's 0. Interestingly enough, we run into a problem here. because the next step would be to divide -4 by 0. And what do we know about dividing by 0? Well, we can't do it. The result is undefined in our real number system. So with all of that work that led up to this, we're going to have to stop here without actually finding a solution. We're going to say that that result is undefined, and primarily it's the reason having to do with this calculation here. We got to this point and recognized that we will not be able to complete that calculation. Therefore, the rest of our result is undefined. Now, I would imagine if we had evaluated h at a different value, say h of 2, we would have gotten a different result. But that's not what we were asked to do. This is what we have. We'll have to stop here. Hope this helps and clarifies the work that we're doing so far. Please let me know if you have any questions with this tomorrow.